Thank you, Dr. Dotto. Uh, Today's topic is a little bit of different. The time-delayed system. As you have probably heard, the time delay means there is some history in the system. The system is not instantaneous. The system actually reminds its past state up to some time. So it is called time delayed. The lecture will be on time delayed system, and in this lecture mainly I shall introduce you the delay differential equation, how it is different from ordinary differential equation, how the delay plays the important role to make a first order system infinite dimensional. As you know, in a first order system, you cannot get oscillation. The system may rest to some point, some stable point or fixed point, but you will see with your surprise that the inclusion of a minimum amount of delay may make the system oscillatory, a first order system. And also, it may bring the system to chaotic regime and hyperchaotic regime. So these are very interesting phenomena, and inclusion of time delay may cause several things and rich dynamics to appear in any system. So first of all, I shall give you a simple example of what is time delay. Probably all of you have seen news channel. In the news channel, suppose there something happened in some place, there is their reporter, and in the studio there is their anchor. So anchor just ask a question to the reporter, and you may notice that the anchor, after his end of his question, the reporter then also listens. There is some time. Okay, then he replies. That is actually time delay, and it comes in communication system. Communication system is a great example of time delayed system. Apart from that, there are many systems. Whatever you want to model exactly, delay must be considered, because there is delay in nature everywhere. I shall come to examples. So time delay arises inherently in natural and artificial systems due to finite signal transmission times, limited switching speed, and memory effects. The presence of time delay makes a system infinite dimensional, and that infinite dimensionality may give rise to various complex phenomena like bifurcation, chaos, hyperchaos, multi-stability, etc. Coupled nonlinear time-delayed system often show very novel and interesting behaviors like synchronization, amplitude death, chimera states, etc. Understanding of which is very important. I am giving one information that a first order system, only one first order system, can even give you chimera state, which is a property of a network. This is the importance of time delay. Infinite dimensionality of time delayed system offers a great opportunity to the researchers to harness the richness of hyperchaos and many more things. And as you know that the Lyapunov exponent is employed here in chaotic system or in other systems. In chaos, there is only one positive Lyapunov exponent, but in case of hyperchaos, there is more than one Lyapunov exponents that are positive. So the complexity of the system is very much. So it may be used as a good candidate for secure communication system. Apart from communication system, you may design some chaos-based noise generator and motion capabilities in robotics, some sensors, etc. For the last few decades, much emphasis has been imposed on exploring the dynamics of systems having intrinsic time delay. Delays are ubiquitous in nature and may be found in physics, biology, mathematics, engineering, ecology, economics, etc. A plethora of natural and man-made systems have been inherent time delay and are mathematically modeled by delay differential equations. Examples include Mackay glass system, optical bistable resonator, that is Ikeda system. Apart from that, population dynamics, physiology, El Nino, southern oscillation, neural network, and control systems. So what is the importance? There are a few practical importance of time delay differential equations, because we need to design it in wishfully in electronic circuits. First time delay system was reported by Mackay and Glass, that was in 1977, but electronic circuit realization, that is in physical system realization, was taken a time of 17 years, because the nonlinearity involved here has closed mathematical form. So that closed mathematical form design is very difficult, and similar case is for Ikeda system. So now we come to the time delayed system. First of all, I shall start with dynamical system. Which you have learned yesterday in the talk of Dr. Dutta. What is dynamical system? Dynamical system, something like x dot is equal to f of x. There may be some parameter, suppose t. The simplest system yesterday shown that x dot is equal to sine of x. So the analysis and geometrical way of thinking was discussed clearly yesterday. Today, I shall take this system to time delay regime and how the time delay comes in the system. Let me give an example. Suppose this is our brain and this is our bone. Brain sends signal to bone to produce white blood corpuscle, WBC, bone marrow actually, and bone marrow creates WBC depending upon the signal. But this signal transmission has some finite time, that is tau. And there is time delay in this system. And that time delay sometimes makes the system unstable. If the time delay increases by some disease or by something, then the white blood corpuscle production in our body oscillates erratically, sometimes chaotically. So if this condition arises, then we are diagnosed with leukemia, that is blood cancer. And this is modeled by Mackay glass. Mackay glass system successfully modeled the leukemia in patients. And after that, several systems has been reported. Example includes Ikeda system in optical resonator. In bistable optical resonator. The form of mathematical form of Mackay glass system may be given as x dot is equal to minus ax, x is a function of t obviously, plus b x tau divided by 1 plus x tau to the power c, where c is of the order of 10. It may vary. And this simple system, first order system with this non-linearity, if we draw, suppose fx tau and tau, then we can get a non-linearity like this. In Ikeda system, the system is represented by x dot is equal to minus x of t plus mu sine x of t minus tau minus x0. So this is the nonlinearity. The form of the nonlinearity is like sine, here f and x tau. So if we come to the physical case, so if we want to study the Mackay glass system, then what we have to control? We have to control the time delay. The control of time delay, that is the delay of the signal from brain to the bone marrow, is very difficult. Externally, we cannot do such control of delay. If we can do, that is very difficult. So if we want to study this system physically, then it becomes really difficult because we don't have the control in our hand, rather easy control in our hand. So what we can do some electronic, as we do in our lab, some electronic analog of this system. If electronic analog is done, then you have some components like resistance, capacitance, etc. If you vary a resistance, then you can vary the time delay involved here. X tau means actually x t minus tau. So by varying simply a resistance value, you can get the effect of variation of signal delay that is appearing in our brain to bone marrow. So the idea is that we are to design the systems which are hard to control in real world system like electronic system, where there is noise, fluctuation, parameter mismatch, and check the validity of the system. Okay, so this is the basic point of time delay system. As you have come to know what is time delay, now let me technically introduce it. To technically introduce it, I have to discuss a little time delayed system. First of all, we define the functional differential equation. Functional differential equation, it is the general form of any differential equation and may be given at x dot means dxt dt is equal to some function of f of t x t plus s cap c, where this is the functional differential equation, and if we discard the s term, then we can get the differential equation, that means dE of the form x dot of t is equal to হচ্ছে t x of t. This is the differential equation. But as you've seen in the example, x dot is equal to sine of x, you need initial conditions at t is equal to t0 or something say 0. What was the initial condition at t is equal to 0? And obeying this sign nonlinearity, how the system evolves. So this is actually initial value problem, IVP. But let me define the delay differential equation. Delay differential equation reads the form x dot of t is equal to f of t x of t minus tau mu, where tau may be real and positive. So this is the general form of delay differential equation. You will go through further. So if we see this system, what happens? This is the time axis and this is the x axis. You know the value of x, that is x0 at time t is equal to 0. And the system may rest to some point for this first order. If there is second order system, x double dot is equal to omega square x minus omega square x, this is SHM, then you may have some initial condition, and depending upon that, you may get oscillations. Okay, so to solve these, we require initial conditions. But in case of time delay system, this is t and this is x. The system not only depends on t, but also depends on minus tau. So this is t is equal to 0, and this is suppose minus tau. Now, if I want to integrate it from here, then I have to know the value of the system or the condition of the system at some previous time, earlier time minus tau. So the history is included in the system inherently. Now integrate it, go to steps. Suppose we consider the step size h is equal to 0.01 and convert it to some integers, suppose 1, 2. Then whenever I come from 0 to 1, then I have to look back from minus tau plus 1. Okay, so I have reached here tau, then I have to read at t is equal to 0. So up to minus tau to 0, I have to provide some initial conditions. Actually, along with these equations, I have to provide x of t is equal to maybe some constant, maybe some function. I am providing function for minus tau less than t less than 0. So this is the complete definition of a time delayed system. And as you see, a small line, whatever be its length, may be considered as a collection of how many points? A small line, how many points it may contain? Infinite number. Then actually we are providing infinite number of initial conditions. And for a first order system, we need only one initial condition. For second order system, we need 2 initial conditions. And in this first order system, we are feeding infinite number of initial conditions. This effectively brings the system to infinite dimensionality. I shall come when I tell the numerical process, then I shall decouple it and write the system, how infinite dimensionality becomes. So this is the essence of time delay, and delay brings the system to infinite dimensionality. Now, depending upon the occurrence of delay, time delay differential equation may be of three types. Number one, retarded DDE. The form is dxt dt is equal to f of suppose t x of t x of t minus tau I. I write here tau I because there may be several delays. Second one is neutral DDE. Neutral DDE. What does it mean? It means dx of t minus tau I dt is equal to f of t x of t plus tau I. And third one is future delay. Future DDE. What does it read? Is equal to f of t x of t x of t plus tau I. So this is the basic types of delay. And depending upon the delay, there are several types of delay differential equations. Let me give example a few, only a few. DDEs with single constant delay. The form reads x dot is equal to f of x, f of t, x of t, x of t minus tau to DDEs with multiple delays, multiple constant delays. X dot is equal to f of t, x of t, x of t minus tau I. Next, DDEs with distributed delays. The form reads x dot is equal to function of t, x of t, integration g to 0 to infinity, g of tau, x of t minus tau dt. The delay is somehow distributed in the system. Next, DDE with state dependent delay. State dependent delay. The form reads x dot is equal to f of t, x of t, x of t minus tau of t, x of t that depends on x of t. And another one, I may say that DDE with time dependent delay. The form reads x dot is equal to f of t, some constant may mu x t minus tau of t. These are some types of time delayed system. So we have described and learned what is time delay. Now here comes the analysis of the time delay. So we have to analyze the system, consider its stability, either it is stable or unstable or anything else. We consider the first order nonlinear retarded type time delay differential equation. And if you ask me about those two, neutral and future, how to consider the analysis, I may clear that I don't know. I only know how to analyze the retarded type of delay. So here we consider x dot is equal to minus a of x of t plus b f of x e minus tau. We can write it minus a x t plus b f of x tau. F of x tau means it is delayed somehow. This function in general may be of any form. You can put it here, the Mackey-Glass nonlinearity, the Ikeda nonlinearity, or any other nonlinearity. But we have considered systems that may be realized in electronic circuits using off-the-shelf electronic elements like resistors, op-amps, etc. So we just didn't use the form like sine of x tau, because design of this nonlinearity in electronic circuit is very much difficult. So we did some tricky things here to get the effect of that. As you know, the form may be like this, to minus pi to plus pi. Okay. So what we considered? We considered a function tan hyperbolic some scaling x, tau something say. So what is the graph of this x tau? Suppose function. How is the time hyperbolic graph? It comes here like this type of, and here we call x tau with some scaling factor and add it with some scaling factor, and it is minus. Okay, so that is some type of this. So in the range of small x, the effect of tan hyperbolic is higher. So it is dominant. So it will come like this. But when x is greater, then it becomes saturated or constant in the negative side also. But the role played by this part. So what actually we get? We get this one. Okay. So this is the nonlinearity f of x tau. We shall consider throughout the stability analysis. You may consider any other form, but we shall consider this form of nonlinearity. You may check that is like sine, that is like Ikeda. Ikeda like. This is Ikeda like system. So we shall consider the stability, and if there is some bifurcation, we analyze those. Stability and bifurcation analysis. So as you seen yesterday, x dot is equal to sine of x, the FP is x star, and for that sine of x star is equal to 0, and you get plus minus n pi. So here also we consider the system as x dot is equal to g of x tau is equal to minus ax plus b of x tau, where f of x tau is equal to minus n x tau plus m tan hyperbolic L x tau. Now the fixed point FP, suppose it is x star, and this is same for x and x tau. So we can get g of x star is equal to 0, because if you do the derivative of a constant point, then it becomes 0. So what we get, or minus ax star plus b minus nx star plus m tan hyperbolic L x star is equal to 0. This condition gives some stability condition. Depending upon the parameter b, n, m, and l, the system may give rise to several fixed points. From that equation, we can get tan hyperbolic L x star is equal to a plus nb divided by mb into x star. If you evaluate it in series and neglect the higher order term and approximate it, then you can get single fixed point x star is equal to 0 for b less than equal to a divided by minus n plus ml. What actually happens? This is the x line, and the nonlinearity just like becomes like this, and you only get the x is equal to 0 point for this parameter condition. And if b is greater than a divided by minus n plus ml, then you can get x star is equal to minus p1, 0, and p1. What here becomes, here you can get this is x, and here you can get the nonlinearity like that. So depending upon these parameters, the form of the nonlinearity changes. So this is 0 point, this is p1 point, and this is minus p1 point. Okay, so this is the conditions for getting fixed points. Now let us check the stability of the fixed points. We have J0. If we want to calculate the characteristic equation, we have to find the Jacobian. We are finding that J0 at x is equal to x star gx x tau del x at x is equal to x star. What does it give? Suppose this is 1 and j tau at x is equal to x star what does it give? Just differentiate it with respect to x tau and you will get b minus n plus ml sec hyperbolic square L of x star. So the characteristic equation becomes so the characteristic equation becomes J0 plus J tau e to the power minus lambda tau minus lambda is equal to 0. This term comes for actually the delay present in the system. And this is a quasi polynomial. And if you try to solve this, then very difficult scenario arises. But we are not going to that difficulty. We are just employing some things here. Suppose it is equation number 2. Equation number 2. So what we get? Lambda is equal to minus a plus b minus n plus ml. Yes, obviously. Obviously. Oh, okay, okay. Actually, we are finding the Jacobians here. Actually, there are two variables, actually x and x depending on tau. Yes, yes, obviously. Two variables actually, x tau. And if you consider the auxiliary equation, etc., then you can get an equation like that. But those are just algebraic steps, so I skipped. Yes. Yes, yes, obviously. That will come in the, what to say, numerical methods. When I shall do, you can see that. Okay. For the present time, I am considering there are two variables, x and x tau. Two variables, obviously. That is actually, if it is two-dimensional, then you can get a matrix, but it is a first order system and one-dimensional. So we are just obtaining this j tau part, and the solution you may consider e to the power mt plus m tau, something like that. Okay, so if you come forward, you can get a equation like this. Lambda is the eigenvalues of that system. Yes, actually here it is a complex value. I shall come in the next step. I don't know. I shall consider. Yes. Of that form. And it will be clear by next steps. Okay. f of xy. Yes, yes, yes.
So then normally in Jacobian we write J is fx, y, gx,
gy, obviously.
So you are only getting then one row of that matrix.
Yes, 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 yes.
How the eigenvalue? Yes, yes.
The eigenvalue we don't know, and we shall see how it comes. Okay.
How did you obtain that 2 is not here? The derivation
For equation 2. Okay. Actually, in G, we have x and xt minus tau. That is dependent on some history. So we have to consider, as you can see the system here, here is x, and in fx, that is x tau. So if I differentiate it with x only, then I cannot get effect of that. If we want to get effect of that, then actually if you do it by 2 cross 2 matrix, then other terms will be 0. Other terms will be 0, and you shall get an equation like this. That is the characteristic equation. If it is not clear, then I can send you the full calculation. Okay. Okay, okay. Then I can send. I just write the extraction here. Yes, yes, yes.
So one row will be complete 0. That s will be J0.
Yes.
And the determinant is 0.
Yes.
Right?
Yes.
So one eigenvalue is obviously 0.
Obviously 0.
I have only one eigenvalue, that is J0.
That is J0, but you have to consider this term as there is time delay. Okay. I am coming. Delayed term. That is just accounted for time delay. Yes. Then sec hyperbolic L x star, because the presence of this exponential term. This exponential. It will vary actually. So this one becomes the characteristic equation here. Suppose it is 3, and we consider case 1, that is stability for tau is equal to 0. Here the characteristic equation becomes simply J0 plus lambda is equal to J0 plus J tau, and lambda in general complex number. So consider lambda is equal to mu plus I nu. We don't know what are these. We shall calculate this. So mu plus I nu is equal to minus A plus B minus N plus ML sec hyperbolic square L of x star, and comparing real and imaginary parts, we get mu is equal to minus A plus B x tau, and mu is equal to 0. So if the system wants to be stable, then the real part of the eigenvalue must be less than 0. For stability, mu must be less than 0. This brings the condition b minus n plus ml sec hyperbolic square L of x star less than a. This is the condition of stability for tau is equal to 0. But interesting scenarios comes when tau not is equal to 0. I shall come to that. Stability for tau not is equal to 0. So, as you know, in the complex real axis and imaginary axis, if this is the eigenvalue mu plus I nu, and it crosses the zone from left to right, then we can say that the system becomes unstable, and obviously here Hopf bifurcations may come. Okay, so we consider the case where mu actually becomes 0. Consider. So this is the limiting case. If we can find the condition where mu becomes 0, then we can get the stability condition from here. Okay. So now our equation becomes lambda is equal to mu plus I nu. So lambda is equal to I nu here as mu is equal to 0, and characteristic equation J0 J tau e to the power minus nu tau minus I nu is equal to 0, or J0 plus J tau cos of nu tau minus I sin of nu tau minus I nu is equal to 0. So again compare real and imaginary part. What we get? We get J tau cos of nu tau is equal to minus of J0, and J tau sin of nu tau is equal to minus of nu. This is suppose number 4. So from these equations we can find J tau square is equal to J0 square plus nu square, or nu is equal to root over of J tau square minus J0 square. Obviously mu must be positive and not negative. So for that mu must be real. So this part must be greater than that. Okay. So this is possible if J tau modulus is greater than J tau this. So in this case our stability condition becomes modulus of B minus n plus ml sec hyperbolic square Lx tau is greater than equal to modulus of minus a. This is 5, suppose. Again, from this equation, that is from second equation of equation 4, we get again from 4. What we get? We get nu tau is equal to no. From the first equation, this equation, we get nu tau is equal to cos inverse minus of J0 by J tau. So from there we can calculate the tau value, how it becomes which leads to tau k1 is equal to cos inverse minus of J0 by J tau plus twice k pi divided by actually nu, and you can get the value of nu from the equation here. So root over J tau square minus J0 square. This is for J tau less than 0, and another set tau k2 twice pi minus cos inverse minus J0 by J tau plus twice k pi divided by root over of J tau square minus J0 square for J tau greater than 0. For these two cases, we can get the tau values or delay values like that. Now, there is a theorem in a paper published in nonlinearity that after some calculation, we can find the stability zone here. Here we have lambda is equal to J0 plus J tau e to the power minus lambda tau, where we may say lambda k of tau is mu k of tau plus I nu k of tau is equal to minus a plus b minus n plus ml sec hyperbolic square L of x tau e to the power minus lambda tau. Suppose this portion as s, consider this as small s, then do d lambda d tau. It gives s e to the power minus lambda tau minus lambda minus tau d lambda d tau is equal to minus lambda s e to the power minus lambda tau divided by 1 plus tau s e to the power minus lambda tau. So if we consider this s is equal to this, then we can get s e to the power minus lambda tau is equal to lambda plus a. From this we can get this, and hence d lambda d tau, it becomes minus lambda lambda plus a divided by 1 plus tau lambda plus a. Now at tau is equal to tau k, lambda is equal to I mu 0 say, and mu of k tau k is equal to 0. Therefore, d lambda d tau at tau is equal to tau k, it becomes nu 0 square minus I nu 0 a divided by 1 plus tau a plus I tau nu 0. Now equating real parts, we can get mu prime tau k is equal to nu 0 square divided by 1 plus tau a third square plus tau square nu 0 square. Hence, it is greater than 0. So there is a lambda. If that is greater than 0, then the stability zone lies between tau is equal to 0. Here we can plot the B, and here tau. We can get some plots like this. This one is tau 01, tau 02, tau 11, tau 22. And there is a lemma that if mu prime of tau k is greater than 0, then the stability zone lies here. So this is the stable zone, and if any value of tau and beta crosses this line, then stability loses and oscillation arises. Now, the direction of Hopf bifurcation may be calculated. Direction of Hopf bifurcation. So for that, I can come to the presentation. Please, presentation mode. So up to now, any question? Okay. Okay. Actually, x star is nothing but the delayed part of x. Okay. So that is a approximation that these two are same. You cannot go further except you do this approximation. It's an approximation that each point of the obviously same as simple OD. Okay. Now there are some terms I don't want to write. There is a paper by Wee on delay differential equation. He has calculated this term and this specially. So after this calculation, you can find I have obtained those equations G20, G11, G02, G21, and other terms W02, W11, E1, and E2. With the application of these, we can just define four terms. C1 of 0 is equal to I0 divided by twice tau 01 nu 0, G11, G20 minus twice mod of G11 square minus G02 square by 3 plus G21 by 2. Mu 2 is equal to minus real part of C1 of 0 divided by real part of lambda prime tau 01. Beta 2 is equal to twice real part of C1 of 0, and T2 is equal to minus imaginary C1 of 0 plus mu 2 imaginary lambda prime T0 divided by nu 0. If you calculate this term, then we can conclude that this is the last part. We can conclude that if number one, if mu 2 is greater than 0, Then Hopf bifurcation. Then Hopf bifurcation is supercritical. Supercritical, and the bifurcating and the bifurcating solution, this part is 0, 1, okay, 0, 1. Bifurcating solution exists for tau greater than tau 0, 1, and obviously the other case, if less than 0, then it is subcritical and tau less than tau 0, 1. Second, beta 2 determines the stability of bifurcating solutions. The bifurcating periodic solution are orbitally asymptotically stable if beta 2 less than 0 and unstable if beta 2 greater than 0. And the third one, T2 determines the period of bifurcating solutions. The periods of bifurcating solutions. Period increases if T2 is greater than 0 and decreases if T2 is less than 0. So in our system, we have parameters 1, B is equal to 1, N is equal to 2.2, M is equal to 1, L is equal to 10, and tau is equal to, suppose that diagram 1.01. We obtain it from this diagram. So upon submission of these parameters, we get 1 mu2 is equal to 14.524, that is greater than 0. That means supercritical Hopf bifurcation. Number 2, beta 2 is equal to minus 11.72, that is less than 0. That is solution are asymptotically stable. And number 3, P2 is equal to 11.142, greater than 0. Period of LC increases. So with that, we can see that in our system, supercritical Hopf bifurcation occurs, and the solutions are asymptotically stable, and period of the LC increases. And by increasing the parameters, we can get a stable state, then an oscillation, then the oscillation goes to period 2, period 4, period 8, and in this period doubling way to chaos, we can get chaos and hyper chaos. So Partha, time is really over. Okay, any question? It seems a little bit of new to you. I did mainly calculation. Tomorrow I shall show you how to solve the equation numerically, because the infinite dimensionality comes. and the coding becomes very hard. Okay, and also I shall describe you how to design these in electronic circuits. So how the delay element may be designed, or how the nonlinearity may be designed. So that's all. Any question?
So how do we know that stability criterion actually works? Like for ODE, so 1D of the system.
Okay.
We do this perturbative analysis and we arrive at stability.
Yes, yes, yes.
When we do something analysis.
Actually, it is done here the same. Okay, but for time delay, the two cases arrows there, tau is equal to 0 and tau not is equal to 0. And for that cases, you can, if you can see the analysis, you can see the condition of stability is obtained. You can just work with that.
But is it obtained the same way?
Almost same way, but the inclusion of time delay requires some special treatment that is done in quasi polynomial equation. Okay. Yes, yes, obviously, obviously. If you want, I can send you another paper, and if you want, this one is the numerical solutions. If I change B like that, B kept B and varied the delay element. So first we get period 1. As I have stated that period increases, period 1, then period 2, this is chaos, and this is hyper chaos. We have designed the system in electronic circuit, and in electronic circuit we obtain the similar scenario. Okay, if you want to further study, then you can consider this book, or you can consider these references. Their detailed calculation are done. Okay. Okay. Yes, yes, obviously. Mr. Sen. In the last calculation, it finds either the system undergoes Hopf or not for tau greater than 0. Some other bifurcations like transcritical saddle node can occur for time delayed system. That may be system that may occur, but in our system, we obtain the Hopf bifurcation. Depending upon system and the nonlinearity, you can get other type of bifurcations. Okay, Mr. Sen. So if, okay. Future delay. That actually depends on some future states. If you ask me furthermore, I don't know very much about it because I didn't work on future delay. Okay, I have just done work in retarded delay, but there is a terminology, future delay differential equation, where the present state depends on some future states. How to calculate the future state, I don't know. There is a system. For the present time, not. If I can find, I can contact you. Okay. Yes. Direction of Hopf bifurcation means with increase of the parameter or decrease of parameter. Here we have obtained with increase of parameter. You can get inverse Hopf bifurcation also. Okay. So in this present case, we can get the Hopf bifurcation with increasing parameters.
The point is that you fix your mu to 1.
Yes.
Now if you increase that mu,
yes.
Then you are going to get the Hopf bifurcation.
Yes, yes, yes. Okay.
If you increase it,
yes.
Then you are only going to stay in the steady state.
Steady state.
I think one confusion still remains.
Okay.
This tau you fix, right?
Obviously.
And then how the partial derivative with respect to tau is happening?
No. Tau is not fixed. We can vary tau. We can vary tau.
But then at some point, but here when you do numerical simulation, tau.
No, not
necessarily. Here it is 1.2.
Actually, for the calculation of these parameters, mu2, beta2, and t2, I consider these values of parameters. This is the nominal value where the bifurcation occurs.
Another question is that the system you have considered,
yes,
it's a bit more complicated.
it is not actually complicated. It is just like Ikeda system, but we wanted to design it in electronic circuit. So the nonlinearity read the form of some tan hyperbolic.
But let's say I just simply consider x dot equals to x into 1 minus x.
Yes, obviously.
Simple logistic equation.
Obviously.
And then can I guess I can perform the similar.
Yes. You can do. You can do the similar performation. I just considered the example because I have done that example. Okay, that work in our research paper. So I considered that very function. You can do any function.
The point is that calculation is not that straightforward like how we do for
without time-delayed system. Time-delayed system and the characteristic equation is here important. J tau e to the power minus lambda tau. That is the determinant.
Just in connection with this question, like if I have a two-dimensional dynamical system which is autonomous,
yes,
and then we have that tau delta diagram.
Yes.
That tau is not this delay tau. The tau is the trace of that Jacobian method.
Okay.
Right?
Okay.
And then based on the tau delta, where delta is the determinant and tau is the trace of the matrix, tau is actually the sum of the eigenvalues, and delta is the product of the eigenvalues.
Okay.
And we have that tau delta diagram.
Okay.
And based on the different combinations of tau and delta, we can have different sorts of equilibrium points.
Okay.
In the time-delayed system, can we have something similar?
You can get some diagrams of eigenvalues here, but we didn't consider it. Okay, you can get, obviously.
So the question is that then, as you said that in the beginning, that time delay basically makes the system infinite dimensional.
Obviously. Yes, actually there is a e to the power minus lambda tau term. If you expand that term, then you can get a large number of terms there. So that considers the infinite dimensionality, probably.
Another question is that I consider simple one-dimensional dynamical system x dot equals to fx.
Okay.
How we have started.
Yes.
And then I consider that there is a time delay which is tau x dot equals to fx tau, right? And then if it is just a one-dimensional system, as we know, we can maximum get stable and unstable fixed.
Yes.
So here you can get a
lot different. So should I write a little thing for 2 minutes? Or okay. So if you want to see what happens, I shall talk it tomorrow.
What is doing to us is that apart from the mode
hyper chaos, obviously.
So that is the only new thing that can happen.
Yes. And not only hyper chaos, depending upon system, you can get multi-stability. You can
that we can also observe
without delay system, but
hyper chaos can also can we get hyper chaos without delay?
Without delay you can get, but you have to consider fourth order system. But here in a first order system, you can get that. So as you asked, if we consider x dot t is equal to f of x t x of t minus tau, and we have to give at t is equal to 0 some initial condition up to tau minus tau. Okay, so we subdivide these sections n minus 1 steps. So total step is n, and the subdivision is n minus 1. So I can give define delta t is equal to tau divided by n minus 1. So depending upon, we can get x1, x2 dot dot xn minus 1 xn is equal to x of t minus n minus 1 delta t dot dot x of t minus delta t x of t. So in this way, the system becomes infinite dimensional. Okay, I shall come tomorrow with detailing of this, how to do numerical. And if you consider this is 4 and we subdivide this by 400, then we can get 400 variables.
So how much the result will vary? If I consider n is 2,
Okay.
right? Still I will get similar sort of numerical result, or there is some kind of finite size.
There may happen some finite size. Okay.
Here the point is that between minus tau to 0,
yes,
you have the option of choosing infinitely many n.
yes, obviously. If we consider a large number, same similar will be some effect of infinite dimensionality you can get.
My question is that how that impact the result of the movement.
So I shall write another line that will be clear. So if we want to do the numerical simulation by Euler methods, x of t minus delta t is equal to x of t plus f of x tau delta t. And if we consider this, x1 k plus 1 is equal to xn of k plus f of xn of k x1 of k into delta t. See, here I have considered x1, that step or the present state, and the past state, and x2 of k plus 1 is equal to x1 k plus 1 plus f of x1 k plus 1 x2 k plus 1 delta t. In this way, I can come xn k plus 1 is equal to xn minus 1 k plus 1 plus f x minus 1 k plus 1 xn k delta t. In this way, you can get n number of variables. Okay. Yes. Okay, I am tomorrow and I am outside, so you can ask, obviously.
I request all of